Alright, this is the Well Delay Pedal, a DBE project found on the DIYGuitarPedals.com.au site. We're going to analyze the circuit here in a minute, but first let's do a little bit of sound sampling. First our clean tone. Alright, and let's just change the level here a little bit. We'll put everything to about 1 o'clock, and let's hear how that sounds. Alright, so that's what it sounds like normally. Sounds pretty good. Let's increase the level knob. Let's max that out, or get close to max. And what the level knob is actually affecting is the loudness of the wet signal. So those delays, those tails, we're going to hear what the what sounds like the post attack becoming louder than the actual attack itself. So let's get a listen to that same piece, but with the level up. Alright, so there you go. It sounds a little bit jumbled together when you have the level too far up. It does have its effects in some places, but I typically like to keep my level more closer to 1 o'clock down to maybe 3 o'clock, but never that high. Well, let's turn that back up to like 1 o'clock here. Now we're going to mess with the repeats knob a bit, and the repeats knob basically tells the PT2399 chip how many times do I want to feed back that sound and repeat it. So the more you have it clockwise, the more repeats it'll spit out for you, and the more you have it counterclockwise, which we're going to do right now, the less it's going to repeat. So I'm going to put it down to like basically a 1, dang near 0. And what this is going to do is now it's not going to repeat so many times. It's probably only going to repeat like once, maybe twice. This is kind of what you want to use when you're trying to do like a solo, or just if you're trying to pick out single notes or a couple of notes at a time, like double stops or something like that. This is kind of where you might want to have it so that it fills in the space in your music right there. So let's give that a listen. So that kind of gives you an idea of what the repeats is doing. So we're going to turn the repeats back up a little bit here. So we're now back to all 1 o'clocks. But this time what we're going to do is we're going to play with the time knob a bit. So as you move the time knob counterclockwise, it actually gets faster between the delays itself. So I'm gonna put this more to straight noon, or maybe even like closer to 11 o'clock. So this should be a little bit faster than what we've been looking at before. So let's listen to how that sounds. Alright, so as you can see, it just basically sped up the gap in time between repeats. Now this can be used to emulate a reverb effect if you crank the time all the way down to like a 1, or maybe like a 2. We'll call it, we'll use clock times here, we'll call it 7 o'clock. And this will kind of, well, maybe more like 8 o'clock. 7:30, whatever you want to call it. But what we're going to do is this will give it kind of a slapback effect, so this starts to get into the area of reverb, echo type effects. So let's take a listen to that and see how it sounds trying to emulate a reverb. Okay, so now what you can do is, opposed to cranking the time down, we can also crank the time all the way in the other direction. We'll max it out here. And this will basically give it a very long space between each of the repeating delays. Now, as we've seen before, with having the level too high, this can make things as well very garbled together. However, when played in a certain way, it will actually sound really good. The scenario that you probably would use having the time maxed out all the way is if you're picking out chords or strumming chords very slowly and you're trying to create some sort of ambience. So that's what we'll do here real quick and give you a kind of an idea of what happens when you max the time out. Alright, and that's kind of a good demonstration there of the Boy and Well Delay pedal. So now let's take a look at the schematic and see what's going on with that PT2399 chip. So here we have the schematic for the Boy and Well Delay pedal. This is a simple PT2399 circuit. Nothing too fancy, just some really good stock values. So let's take a look and see what's going on and why these values are the way they are. Firstly, we'll go with the power supply. We have a reverse polarity diode so that people don't plug in things incorrectly. Then we have a voltage divider here that sets a bias voltage reference for the op amps that are to come up later in the circuit. We have a linear regulator here that steps down the 9 volts down to 5 volts. This is to make sure that there's a 5 volt rail provided for that PT2399 because that's what kind of voltage it runs on. If you were to try to give it something like 9 volts, it's going to go up in smoke. So keep it at 5 volts. And then we'll take a look and see what we got here for the guitar signal. So for the guitar signal, we have a input, gain, and buffer section. We have an anti-pop resistor here with a 1 mega ohm resistor. We have a high-pass filter just to basically block out DC paralytic noise. This right here will block out about 4 hertz if you do the math against it. And then we have a inverting op amp here. We can tell by R11 and R12 that the gain on here is simply 360K over 180K equals a gain of 2. Not that much gain, but still some there. Also, right here with C16 and R12, we have a low pass filter that if you look at it, the low pass is basically cutting frequencies above 9.5 kilohertz, we'll say. But yeah, that's basically just to shave off the highs and the harshness. So after this, you can see that we have a dry signal that goes into another op amp, but we'll get into that in a minute. Primarily what we're going to look at now is the whole what's going on with this PT2399. So this line right here is the input line, and then this line that's coming out this way, this is the output line, which will go into that op amp later. So let's break down this PT2399 into some smaller chunks that we can read here. Now, if you've gone to electrosmash.com, that's actually where a lot of my resources on this has come from as well. But there are some other sites that have helped out as well. The only thing is on the Electrosmash, it just gives you the chip. It doesn't have any references to the supporting electronics to go along with it, which is what this is going to kind of give some answers to. So firstly, we have pin 1. Pin 1's the power supply. We already explained that. We're going to be giving it 5 volts. Pin 2 is a reference pin for an internal voltage divider. You can kind of look at this capacitor here being the same kind of capacitor that you would use over here with our voltage divider to provide bias to the op amps. You always will notice that there's a slightly hefty capacitor decoupled with that. There's that kind of circuitry going on inside that PT2399. It's just they didn't have enough room, I'm going to guess, or just felt that it was necessary to make you guys put the capacitor in here as opposed to them putting it inside the chip. But there again, you just slap yourself a decoupling capacitor right there. Now, the interesting parts are pin 3 and pin 4. This is the analog and the digital ground. You need to basically give a short trace to ground to these guys between each other, kind of in a star configuration, if you will. The idea is going to be that internally, there's like a little 10 ohm resistor that go between these two pins. That's just basically how they laid it out to make it do all the stuff that it needs to do, because there are some digital components inside of here, like comparators and whatnot, and then there's some analog components in here, such as op amps and high and low pass filters. Now the next pin that we have here is we have the pin 5 clock output. Now, a lot of people don't really use this pin because it's just a means of getting feedback information from the PT2399. But if you were trying to design a circuit that wants to sync the delay to something external, such as like a tap control device or a microcontroller, this is a good way to kind of get that feedback information. What this guy will do is it'll provide a square wave that's based off of your delay time. So as your delays get shorter and shorter, it's going to make a tighter and tighter frequency square wave, and as you go longer and longer and longer, it'll have a wider, lower frequency square wave to take a look at. So now let's take a look at pin 6. So pin 6, this is actually how we control the voltage control, the oscillator that's inside of the PT2399. It's just a resistor that goes to ground. Now, what most people do with their delay pedals that are PT2399 based is they'll put a potentiometer here. In this case, we have a 50K linear potentiometer there. So you have 50K plus this little 2.7K in series. The reason we have that 2.7K resistor there is when the PT2399 powers up, if it sees something around 2K or less in resistance for that first half a second that it's booted up, it has the potential to lock up and then just not work until you power down and power back on again. So to prevent that lockup, we just make sure that it has a little bit extra resistance at startup at all times, and then it's fine. So the idea with the resistance in this clock is the lower the resistance, the shorter in times the delay. So if you want like slapback, reverb kind of stuff, then that's when you're looking for basically that minimum 2.7K resistance, and then that's it. The larger the resistance, the longer the delays will be, but at a sacrifice of distortion. That's basically it. The longer you delay it, the more distortion gets injected into the signal. So technically, there's RAM limitations to the insides of the PT2399, but just using hypothetics, if you set the resistance to something stupidly high, like, I don't know, 1 mega ohm, then it's like, well, yeah, it's going to repeat with the spaces in between the repeats. Could be minutes in between, but it'll be so distorted that it won't even be recognizable as an audio signal. So that's not how that works practically, but that's the idea. Where it actually starts to cut off is probably around 600 milliseconds of delay between gaps. It starts to get pretty distorted. And there's a chart in the build doc that shows what the varying resistance values will give as a delay time versus how much distortion that's going on. However, if you really want to nerd out a bit, there is actually a calculation you can use to figure that out. It's also in the build doc, but you can take any resistance values and then punch them in and basically come out with the milliseconds exactly as what it should be. Although I will say, bear in mind, remember these resistance values have to be exact, and it's really hard to get resistors to have that good of a tolerance, especially with potentiometers. But if you know what the pre-existing resistance is, for example, you're using a digital resistor hooked up to a microcontroller like you would on a tap tempo, tap flow type circuit, then you can kind of figure some of this stuff out. Okay, so now let's look at the input signal that's coming into this PT2399. So the PT2399 has integrated components inside of it. That's why it's called an integrated circuit. And one of the integrated component sets that's in here are op amps. There's 3 of them. 2 of which are pretty much hard set internally. Nothing you can do with it, including the whole capacitors, resistors, and everything set to them. But the 3rd op amp, we have the ability to attach external components to and change the values. So what a lot of people do with their delay circuits is they'll use this to create a multi-feedback low-pass filter topology. So the idea is going to basically say, all right, any frequencies above this, don't even try to process these because it's not worth it. Whatever you define not worth it to be. How we do that is we have the values for R8 and R9, and we have the capacitors C13 and C14. And if you look at the build doc, it'll get more into the actual specific equation that you want to punch in, but this will come out to calculating a cutoff frequency of just a hair under 5 kilohertz. So anything over 5 kilohertz, don't worry about processing because we don't need it. Once you start getting into those higher frequencies, it's going to be kind of tinny when you try to delay it, and it just doesn't sound that good. It doesn't sound musical. Alright, so now let's take a look at C8 and C9. These are the output stage components for the PT2399, those 2 op amps that we really can't touch. Well, these we can, but that's about it. We can use these to create low-pass filters to reduce unwanted high frequencies. The typical value that you really see in there is 100 nanofarad. For if you're trying to do delay, if you're trying to go more echo, then you can cut it down to 82 nanofarad. Actually, if you really want to go really short slapback delay to get those natural harmonics to shine through, you can go as far down as like 22 nanofarad. However, for longer delays, like 300 millisecond delays, you don't want to go anything lower than 47 nanofarad. So using the 100 nanofarad, that's just basically a good safe value. But if you were to do the math on the low-pass filter, with 100 nanofarad, it's basically cutting around the 1 kilohertz frequency point for those delays. Alright, and then after leaving the output here, we come up to R7 and C12. This creates another low-pass filter, cutting frequencies above basically 16 kilohertz. Unfortunately, the drawback to this is it actually also raises the output impedance of the circuit, but don't worry, we take care of that here when we have an output buffer. That's why we have an output buffer. And then we also have a decoupling capacitor here at C21. So basically any large value, 1 microfarad all the way up to 10 would be fine. So now we come up to here. This is where we have our repeats or our tails and then our general level. The idea is repeats is feeding back into the system, and this feedback is being grounded out. So if you want fewer repeats, you create higher resistance to the point where you ground out that signal and it won't feed back as much. And if you ground it all the way out, then it can't feed back at all, cutting all the repeats out of the thing. We also have a level potentiometer here. So this is the wet signal, ultimately, at the end of the day, leaving, including all the tails that are attached to that output signal. But this is just the wet signal, not the dry. And as you drop the level on this, it's just killing out the wet signal and grounding it out. Kind of like a volume potentiometer you'd use on a regular, like, distortion or overdrive pedal. You're grounding it out to get rid of the noise, which then comes up to a decoupling capacitor. And now we get into our output buffer, and that will be the end of the circuit. Alright, and this is the last part. This is the mixing stage, or the output buffer, depending on what you're looking at here. The idea is it is a mixer because we have our dry signal coming in across R13, and we have our wet signal coming across R15. So this is the dry signal, this is the delay signal. I would say that the mix ratio would be 1:1. However, you can see that the resistance values between R13 and R15 are different. Because of that, it's more like a ratio of 1.1 to 1 in favor of the delay signal, just because it's got a lower resistance. So, like the input buffer that we have right here, the output buffer is a inverting op amp, because we can see the signal coming in on the inverting pin. Also, like the input buffer, we have a low-pass filter between C19 and R16 that's cutting around 132 kilohertz, if you do the math, which you can find in the build doc. I know that's a really, really obnoxiously high frequency, and there really shouldn't be a reason to cut that high, but there are harmonics that we're also trying to cut as well, and those harmonics will residuate down. From here, we also, the other reason too is because of the resistance right here to here, we're trying to keep the gain close to unity, but maybe not quite. So from here, we have our decoupling capacitor, and then from there, we have a high-pass filter, which is basically cutting out low-frequency DC parasitic voltage, somewhere around the order of 1.5 hertz. So that's basically what we got right here. One other thing to note, I know we said earlier, we have this issue right here of output impedance. With this filter, it kind of raises that value up, which is not so good. And I said later that we would solve it up here in this buffer, which we do. The output impedance is based off of the op amp we have here, and R17 and R18. And if you take a look at the build doc, you'll see the more specific maths, but basically this will give us an output impedance of 1K, which is good. You want to try to keep in design an output impedance of 10K or less, so that it plays nicely with the pedal that comes after this one, if there is any, and then of course the amp itself. So that's basically what's going on with the circuit. It's a simple PT2399 delay, nothing too complicated, but what is nice is once you understand how the chip works and you have some example values to play with, which you do with our boy and Well, you can determine things that you may want to change and customize. So maybe you don't like the delay range that's set here. Maybe you want to change how some of the filtering is done. All these resistors and capacitors can be changed to cut out or add harmonics and other frequency points that you may want. If you find out that you don't like the volume on the thing, you can always change the gain structure here or the gain structure in here to increase or decrease the volume. You can also do things like chop that guy out right here, R18, put in a volume knob if that's something that's desired. These are all options that you can do with the delay pedal. Lots of things you can customize. Alright, and that's all that we have for today. If you need more of the math explanations, you can go into the link in the description for the build doc. If you like these kind of videos where we go over the circuit analysis in a little bit of more detail, just let us know in the comments below, slap like now, and subscribe. If you want to support us, just go to our website, which is www.diyguitarpedals.com.au, and purchase a couple PCBs or kits. Right now it's a good time to get into a hobby, considering that a lot of people are on lockdown and don't have much to do at their homes. So here's an option for you guys to go brush up on your soldering chops. Anyways, just let us know what you think. Thanks. Cheers.